And we should be live. Let's just get it started on TikTok. And we should be good to go. We'll be starting in just a minute. I just have to get things set up. And then we should be all set. Please be patient. All right, we should be good on TikTok and on YouTube. We're just gonna give it a little bit of time so then we can wait for people to trickle in. How's the size for everybody who's watching on TikTok or on YouTube, or is it too small? Because I can't really make it bigger. Well, actually, maybe I can. Let me try something. There's always the HTML format, which might be able to make it bigger. Yeah, how's that? I can make that a bit smaller. How's this? Is this visible on TikTok, on YouTube, on wherever you're watching? Thank you, Grimlock, for the $5, as always. This is good? Okay, great. So I will use the HTML. I've never used the HTML format before. I wish this beta bar... I wish the beta bar would go away, but... Oh, that's terrible. Why is that 2 so big? That's fine, I guess. Today, we're doing a peer review. So I haven't done this in a while because I've been busy, I've been away. But what we're going to do is we're going to review a new paper that came out, in this case, like, I don't know, a week ago? And we're going to take a look at it. Now, almost certainly, this paper doesn't need my peer review. This isn't an official peer review, by the way. Almost certainly it doesn't need my peer review because this particular paper won 5th prize in the Gravity Research Foundation 2025 Awards for Essays on Gravitation. So every year there is a, the Gravity Research Foundation has an essay award contest. And this is where kind of, in some sense, more philosophical, not quite philosophical, but like kind of more foundational papers will often appear. Essays, you might even call them. They do have math in them, of course. But you're going to find like kind of more, in my view, more interesting papers in these essay contests. Whereas many of the papers that end up in publications like normal general relativity or cosmologist papers, these are much more technical than these kinds of things. So these make for very good, interesting papers for live streams. Grimlock asks, are you returning to the desert or going somewhere green? No, I'm returning to the desert. Should people study loop quantum gravity? If you want to, yeah, you should. So, okay, so we got enough people. I think that we should probably start. How's my audio? Is it loud enough on YouTube and on TikTok? Anybody? Confirmation would be great, and then we can get started. Howdy, howdy. Okay, so we're good on TikTok. Should probably be good on YouTube. All right, so let's get started then. So the paper is entitled Space Cannot Stretch Too Fast, which is a great name, by Samir Mathur, Department of Physics. I don't know, maybe he's a, I mean, he's at OSU, maybe he's a postdoc, maybe he's faculty, who knows. There is no guest. There is no guest here. I'm not talking to anybody, I'm talking to you guys. So, why don't we just read it, and Oh yeah, I need to send out the Discord announcement. Thank you for the reminder. I always forget that. Thank you. Thank you so much. Right. Okay, but let's get started. So, yeah, I do have a PhD and a postdoc. I just finished my first postdoc, actually. So we argue that this paper is going to argue that black hole microstates leave an imprint on the gravitational vacuum through their virtual fluctuations. This imprint yields a power law falloff. So to be clear, all of these terms will hopefully be explained in the essay. However, I can briefly explain. So black hole microstates are just possible ways of arranging a space-time at like the microscopic level that you end up with a black hole. So they're saying that black hole microstates leave an imprint on the gravitational vacuum. So this is the normal empty gravitational field through their virtual fluctuations. So because we're talking about microscopic black hole stuff, there can be quantum gravity stuff happening. So that's the claim here. This imprint yields a power law falloff rather than an exponential falloff for the entanglement of Planck scale fluctuations at different points. So you could have fluctuations occurring at different places that can be entangled with each other. These entanglements generate an extra energy when space stretches too fast, since causality prevents a relaxation of these entanglements to their vacuum values. So if space stretches too fast, that entanglement can't really like come to rest before they get too far away. We obtain semi-classical dynamics for slow processes like star formation, but a radical departure from semi-classicality when a black hole horizon forms, even though curvature remains low everywhere. This resolution of the information puzzle also implies an extra energy source at the scale of the cosmological horizon, which may explain the mysteries of dark energy and the Hubble tension. So that's why this is an interesting paper, at least in my view. I haven't read it yet. Maybe I won't understand any of it, but they're at least making the claim that this kind of entanglement of microscopic black holes could potentially resolve the dark energy problem. And you know me, I care deeply about the dark energy problem. So let's just read. It's not so long, I think it's 11 pages, and it's double spaced, so much shorter. Galileo and Newton focused their study on material bodies, which were imagined to move through an inert, featureless vacuum. But further progress has indicated that unlocking the secrets of nature requires a better understanding of this vacuum itself. Sorry, I'm going to drink some water. Einstein's gravity taught us that the vacuum has a shape. Small ripples in this shape describe gravitational waves. So far, so good. Quantum field theory taught us that the vacuum is full of virtual particles. That's a little bit of a lie, but it's okay. Which emerge as the real particles of Hawking radiation when space stretches during gravitational collapse. Cool. For those who are just joining us, today we're doing a peer review. We're reviewing a new paper that came out recently in the physics literature. In particular, this paper is entitled "Space Cannot Stretch Too Fast." If you Google that, you'll find it. But this phenomenon of Hawking radiation leads to the information paradox depicted in Figure 1. Let's go take a look at Figure 1. So here's Figure 1, a semi-classical picture of gravitational collapse in Eddington-Finkelstein coordinates. I'll explain that in a minute. A shell collapses to a point generating a singularity. Space-like slices in this geometry stretch more and more as time evolves. This stretching leads to the creation of entangled pairs as a resulting information paradox. So, the idea here is they didn't actually like label what A, B, and C are, but I'm sure that they'll go into it. But so here, this triangle, this cone thing, that's the matter that's falling in, and then it collapses to this line here. That's the singularity. And then the dotted line is the event horizon. So you can tell that the dotted line is the event horizon because these little mini cones that are tilted, those are the light cones, and so that's the place where stuff can only fall in. So here we have Hawking radiation going in and out. And so I guess they're not really illustrating it particularly well, but they'll probably talk about it more. suffice it to say, what I suspect they're going to say is that, and you know, these are labeled, so we'll talk about it more, but what they're going to say is that we have an issue of how does the information come from within to get without, right? That's the information paradox. This is not an apparent horizon. This would be a genuine horizon, right? Assuming that it's an event horizon, assuming that there's no Hawking radiation, of course, right? Wow, we really brought the flat earthers to the live. I don't know why they show up for the peer review, but anyway. So the good slices in the classical black hole geometry have low curvature everywhere. I think that those are probably these slices, these curvy ones here. Time evolution leads to a stretching of these slices, which in turn leads to the production of entangled particle pairs and the consequent monotonic rise, that means rising in one direction, of entanglement between the radiation and the remaining hole. So the point is as this Hawking radiation gets sent out, the Hawking radiation is entangled on the outside, is entangled with a black hole on the inside. That's the claim being. And so as more and more Hawking radiation is sent out, the amount of entanglement gets bigger and bigger, monotonically. It increases without ever decreasing. The small corrections theorem has provided a rigorous version of this conflict. I'm actually not familiar with the small corrections theorem. Let's Google it. Let's find out. Small corrections theorem proves one needs order unity corrections at the horizon. Oh, this is by the same author. Okay. Let's just take a look and see what this has to say. Presumably, they will bring up the small corrections theorem. Ah, okay. I think that, wait a minute, hold on, where is the bit about the small corrections? Ah, it's these. These are the small corrections. So there's extra stuff that you have to do to account for the entanglement of between the black hole and the Hawking radiation. Right, the small correction theorem has provided a rigorous version of this conflict. If usual semi-classical physics, so semi-classical physics is basically, it's what happens when you do regular quantum field theory, but in a curved spacetime. That's semi-classical physics. If usual semi-classical physics holds at leading order around the horizon, then there is no way to prevent this monotonic rise of entanglement. So this is to say, the monotonic rise of entanglement is not good because there's some information loss, right? Thus, if information is to be recovered in the radiation, then there must necessarily be a second mode of failure of the semi-classical approximation. One at low curvatures distinct from the failure when curvatures reach the Planck scale. So basically, there has to be something that cancels out that cancels out or ruins the semi-classical approximation. That's the business. And so I think that that's what they're going to propose. Let's see what they have to say. So in this essay, we will see how a further fundamental change to our picture of the gravitational vacuum will resolve this long-standing puzzle. The role of non-perturbative vacuum fluctuations has been noted, but a crucial recent insight about the entanglement structure of these fluctuations leads to the complete picture described below. So non-perturbative vacuum fluctuations are like not small. So vacuum fluctuations are just the vacuum doing quantum things. Non-perturbative vacuum fluctuations are when those quantum things cannot be treated as like just a small little deviation, when they're significant. Remarkably, this resolution implies a failure of Einstein's equations at the scale of the cosmological horizon as well, something that may account for the mysteries of dark energy and the Hubble tension. That's a big claim, probably why this paper won 5th prize, but we'll see what they have to say. Right. Always remember to hydrate. Yeah, this paper won 5th prize. I actually read the paper that won 1st prize. I read it this afternoon. And honestly, I don't think it's very good. Or no, sorry. The paper I read was runner-up to 1st prize, so it got 2nd place. But still, it really wasn't very good in my opinion. Like, I think it made some very trivial errors that like anybody with the training in like, I don't know, mathematics would have caught. like foundational mathematics would have caught. I could be wrong. Like, you know, it's the people who wrote it are no slouches, but like, anyway. All right, let's continue with this paper. To describe quantum field theory, we take a lattice of points. We take a lattice of points. So what we're doing here is they're going to talk about quantum field theory. So we have to do it. So a lattice of points is just, instead of having a continuous space, or a continuous space-time rather, you just break it up into a grid, right? So you take a lattice of points, that's what the grid is, assign a field variable, a spin, a scalar phi of x, or something else. So you're just assigning a value at each point. And choose an interaction between the variables at neighboring points. So at each point you have a variable, or something, maybe it's the spin, or maybe it's the, whatever it might be. And then you just say, well, when two nearby points, or when 2 points are nearby each other, they can interact with each other. They can change each other's values. That's how you do quantum field theory. Gravity requires an obvious modification. The number of lattice points must increase when space is stretched. Kind of checks out. With this modification, we obtain quantum fields on curved space, which imply phenomena like Hawking radiation. Fine, no issue there. But this cannot be a complete description of quantum gravity, since the states of quantum fields cannot reproduce the exponential of the Bekenstein entropy microstates of black holes. So all this is saying is that the number of possible ways that a black hole can be arranged, that's what a microstate is. The number of possible ways that a black hole can be arranged, or that the microscopic pieces of a black hole can be arranged to give you the same kind of macroscopic black hole, is this number. So it's the exponential function, so it's E, Euler's number, to some power, and that power is the entropy of the black hole. So here it's the Bekenstein-Hawking bound, that's what S sub Beck stands for. So that value is the area of the event horizon divided by 4 times Newton's constant. This is the Bekenstein entropy. So this is a huge number, by the way, because you take the area in, I guess it's in natural units, so in Planck units. So you take the area of the surface area of the event horizon, you divide it by 4, and then you ask how many Planck areas fit into that surface area divided by 4. And it's going to be an enormous number, like 10 to the 50 or 10 to the 80 or something. Yeah, what is a Planck area? Let's look up. Just so we can get it, just so I can put a number on it for you. So a Planck area is 2.6 times 10 to the minus 70 square meters. And if we take a, what is the surface area of a stellar mass black hole? The surface area of a stellar mass black hole is, here we go. I guess it's just proportional to the mass squared, right? But we should probably be able to get a number from this. Well, okay, so we know that they're like roughly they're like a few kilometers across. So let's just say it's a few kilometers across. So that would make their surface area 4 pi r, so it's like 10 times, yeah, so it's like 10 times a million, so it's like 10 million. So take 10 million cubic meter or square meters. Heisenberg, congrats with your physics degree. Take 10 million square meters, divide it by 4, and then divide it by 10 to the minus 70th. So the Bekenstein entropy is like roughly 10 to the 77 for like a stellar mass black hole. And then you take E to the 10 to the 77. So it's a huge number of microstates, like a genuinely enormous number. Like E to the 10 to the 77, right? But that's how many microstates there are for a black hole. And importantly, the quantum fields can't reproduce that many different states. So we need something more complicated than just a simple lattice model. That's the point. So first consider electrons and positrons. This is how we're going to handle it. So these exist as real, i.e. on-shell particles with energy mc squared. This is fairly, this is just basic Einstein stuff. As a consequence, the vacuum with zero energy contains virtual fluctuations corresponding to these particles. That's a lie. It's a little bit of a lie that we tell because it makes for good calculations, but like these virtual particles aren't real. But these particles also form a bound state, the positronium. Positronium is just what happens when an electron and a positron form a sort of atom with a radius of one angstrom. So there's a bound state. There's like an atom made of a positron and an electron. And so the question is does the vacuum wave function... Sorry, I have the hiccups. So they ask the question, does the vacuum wave functional have virtual fluctuations of positroniums? Not just a positron-electron popping into existence and then reannihilating, but can they pop into existence, form a bound state, and then reannihilate virtually? A moment's thought, sure. An angstrom is 1/10 of a nanometer, for those who don't know. Right, so a moment's thought indicates that including virtual positronium would be overcounting. Okay. The way the positronium manifests itself in the vacuum wave functional of quantum electrodynamics is through correlation between the positions of virtual electrons and positrons. The configurations where the virtual electron and positron are 1 angstrom apart have a slightly higher amplitude since the energy of such configurations is slightly lower, meaning when they pop into existence, if they are 1 angstrom apart, then they form a bound state, a virtual bound state, and because it's a bound state, they have slightly less energy because they have their potential energy is lower, and so it's slightly more probable because it takes less energy to do so. Similarly, other bound states of the standard model, like the benzene ring, lead to subtle correlations among fluctuations of the elementary fields in the vacuum wave functional. So this is just saying that you have small calculations from having a bound state. Anytime that something forms that could be like stable, at least mildly stable, that has a slightly lower energy, and thus you have a slight increase in the probability of that state arising because it takes slightly less energy to spontaneously pop out. Again, this is all in the picture of virtual particles, which is not really an accurate picture, but it's a good way of thinking about things. Okay, this picture, I'm sure this diagram will be useful later. Now, this is probably reasonable. We do not often worry about these subtle correlations because they are small. But could there be another class of bound states that we have forgotten? Yes. Yeah. So virtual particles are absolutely a good way to calculate. Yeah, they're just not real. But could there be another class of bound states that we have forgotten? Yes, there are e to the 10 to the 77 black hole microstates for each value of m, with m between 0 and infinity. So there's a lot of possible black hole microstates. These microstates are bound states of the elementary objects in our quantum gravity theory, and must leave their imprint on the vacuum wave functional of quantum gravity through correlations of the kind mentioned above. So the point that they're getting at is that you have, so in quantum electrodynamics, that's the quantum field theory for electromagnetism, for electrons, for photons, and these things. You have these bound states that can pop in and out of existence, and those are slightly more likely because they have slightly less energy. But they're usually small because there's just not very many of them. However, when you have slight vacuum fluctuations in the gravitational field, well, the vacuum fluctuations that include black holes, because you can have microscopic black holes that pop out, there are an ungodly number of such possible vacuum fluctuations. So even if the contribution of each one is small, the number of them is quite huge. And so what it seems like they're saying is that, yeah, we do have to worry about this. This could actually affect the gravitational quantum, or the quantum gravitational vacuum. So I guess that's where they're probably going to go. To understand this vacuum imprint, we must first know something about the on-shell microstates. Again, on-shell microstates are like the real thing, so like the real black holes in this case. In string theory, all the microstates which have been constructed have turned out to be horizonless objects called fuzzballs. Horizon-sized quantum balls made of the fundamental objects in the theory, strings and brains. A toy model of fuzzballs will be useful in extracting the essential properties we need. Okay, so they're going to be relying a bit on string theory here, but we'll let it happen. In figures 2a and b, we depict schematically the compact and non-compact directions. Small fluctuations of the compact directions yield the light particles of theory. So remember, in string theory, you have compact dimensions, these are the curled up extra dimensions of string theory. In string theory, it's 6 extra dimensions, right? And so there's 4 non-compact directions or non-compact dimensions. They're the ones that we move in, right? There's the 3 space and 1 time direction. And then there's the 6 compact directions. So let's go look at figure 2. So in figure 2a, we have small definite deformations of the compact directions give scalar fields. So I guess going from here, this tube, to the not tube, sorry, the small deformations of the compact directions are just the tube. So I guess we have slight deviations. Rip Steakface for the $15. Thank you. Much love, Mr. Dr. Professor Blitz. I appreciate you. So small deformations of compact directions give scalar fields. It doesn't really follow from the picture, but you can see how it's like oscillating in and out because it's getting bigger and smaller, right? And then they have larger deformations create Planck scale solitonic objects like Kaluza-Klein monopoles. That's a mouthful. But this is just saying that you could have splittings actually occur for the non-compact dimensions. And then I guess this is the microstate for a black hole in string theory, a complicated bound sets of such non-perturbative objects. So they're just kind of like these tubes that can like stretch and they can wiggle and wobble and all of this business. Fine. Oh, this is going to get involved. I can already tell. Okay, well, let's keep reading. If we get stuck, we get stuck. It's fine. That's totally normal. Not everybody can read every paper. Right. In figure 2a, 2b, we depict schematically the compact and non-compact directions. Small fluctuations of the compact directions yield the light particles of the theory, but we can also have larger fluctuations that pinch off, that's what we just saw, a compact direction to yield non-perturbative solitonic objects like Kaluza-Klein monopoles. A microstate for the whole of mass m has the form of a bound state of these monopole-like objects, with overall radius 2gm plus epsilon. So the size of the fuzzball, which is the string theory version of the black hole, is just slightly bigger than the event horizon. So there's actually no horizons for black holes, for string theory black holes anyway. The various fuzzball constructions bypass the usual no-hair arguments due to the special features of string theory. So don't worry about that. It's just a kind of like an aside. And the fact that the compact directions are not trivially tensored with the non-compact ones in the interior of the fuzzball. There's a question, so does the Bekenstein bound limit information truly, or is it just an assumption, or I may be mistaken? It's kind of, I mean, in some sense, it's like something that's been theoretically proven, if that makes sense. All right, let's keep reading. While the on-shell fuzzball microstates of black holes are relatively well understood by now, not by me, but by other people, our present goal is to model the effect of these bound states on the vacuum wave functional. Yeah, that's what we were talking about earlier. Using our above schematic description of fuzzballs, we can develop a picture of what the quantum gravity vacuum should look like. Is this it? Is this what it should look like? Oh, no. This is just yeah, okay. So, it is generally agreed that there will be violent fluctuations of spacetime at the Planck scale. Yeah, I agree. In fact, this is something that I wrote about in a paper last year. We can make this more concrete using figure 2. What about figure 2? At the Planck scale, we have not just fluctuations of massless fields as in figure 2a, but also the topology changing fluctuations of figure 2b. So, if you just wiggle this tube, it doesn't change much. But if you change the tube, if you like cut it in half, that's a big change. And so that's what they're talking about when they say topology changing fluctuations. And these generate the non-perturbative objects of string theory like KK monopoles, Kaluza-Klein monopoles. Fuzzballs involve these non-perturbative objects in a fundamental way. So to capture the effect of virtual fuzzballs, we place a monopole-like non-perturbative object at each site of our Planck lattice. Place a monopole-like non-perturbative object at each side of our Planck lattice. Okay. Okay. We'll see what they have to say. The non-perturbative objects of string theory form 256-dimensional spin multiplets. Yeah, that's true. But for simplicity, we will attribute spin 1 to the object at each site. That's pretty funny, not gonna lie. In figure 3a, so this should be 256, by the way. Well, okay, no, it should be like whatever 256 divided by 2 is, 128 or so, or spin 127 and a half or something. So, but they're just gonna simplify it. It's fine, no problem. In figure 3a, we depict a one-dimensional space-like slice with these non-perturbative objects at lattice sites depicted by black dots. So S1 and S1 prime are spin 1 objects at neighboring sites, and S2 and S2 prime are another such pairs of objects at sites further away. So the idea is like, if you made your whole black hole one-dimensional rather than three-dimensional, this is what it would look like. You would have some lattice sites that can interact with each other. Each one of these is a non-perturbative object placed on the lattice. So S1 and S1 prime can interact, S2 and S2 prime can interact. Fine. And in principle, I suppose, that pair could interact with this pair via some other interaction. Presumably they're going to get to that. So that was one feature of what the picture of what a quantum gravity vacuum should look like. You like when they get bigger, so do I. It's quite nice. Now, this is the second feature. Recall that the on-shell positronium had a size of 1 angstrom, and its impact on the vacuum wave function was to correlate fluctuations that are 1 angstrom apart. The on-shell fuzzballs are extended objects with radius 2 gm, with m being, so g is Newton's constant, m is the mass of the fuzzball, and m ranges from 0 to infinity. So their imprint on the vacuum will be in the form of correlations across all length scales. So because they're just reasoning by analogy here, the positronium, the correlation between 2 points in space was related to the size of the positronium, which is about 1 angstrom. So the correlation between space-time points in a quantum gravitation, is that linked to 2 gm over r? No, not really. This is the Schwarzschild radius. So the correlation between space-time points should be arbitrary, because you can have arbitrarily large black holes. In quantum theory, correlations between two sites are given by an entanglement, and that's the key point. An entanglement between states at these sites. These correlations should follow up with distance, so we want a large entanglement between nearby sites and a smaller one between more distant sites. Do you ever host a beginner's live on physics? Yes, that's every Wednesday, or at least it's supposed to be, in some sense anyway. Such an entanglement, decreasing with distance, is schematically illustrated in the one-dimensional picture of figure 3a. They're going to explain it, and then we'll go up and look at the picture. Let the spins at the neighboring sites, S1, S1 prime sites, be entangled to produce a state. This is the name of the state. So it's 1 minus delta squared times S1 plus delta T1, where S1 is the singlet made out of the 2 spins, and T1 is the triplet. So imagine they have two quantum tops, right? And they're spinning. So each quantum top, they could either both be spinning in the same direction, they could both be spinning in opposite directions, or they could be spinning in a combination of opposite directions, right? So the singlet states and the triplet states correspond to different combinations that they can be in, essentially. The singlet state is one where they're in opposite directions with a minus sign, and the triplet states are where they're in the same direction or in opposite directions with a plus sign. It's kind of a technical detail. It's not super relevant. But importantly, this is just the description of the entanglement of the state. Similarly, the neighboring spins, S2 and S2 prime, are entangled in the same type of state. Finally, we entangle the 2 triplet states to make a singlet, S. So when delta is small, so you can take 2 triplets, either both up, both down, or half up, half down, and you can entangle them with each other to make another singlet. With delta small, we find that each site is strongly entangled with a neighboring site, but there's also a smaller entanglement with sites further away. So if delta is small, then so imagine that delta is small in this formula here, right? In this formula, if delta is small, then you basically just have S1, and you basically have none of T1. which means that you mostly just have singlet states between neighboring lattice points. But of the little tiny bit that is a triplet, those can entangle to make another singlet, and so the actual entanglement between the distant sites will be even smaller still. So that's that's kind of what they wanted to get. They wanted to get that the entanglement between nearby points is large and the entanglement between far away points is small. Now, that's a one-dimensional picture, right? So here we have the here we have on the left we have the two neighboring states that are highly entangled. On the right we have two more neighboring states that are highly entangled, and then between the two we have a weak entanglement. That's the whole point. Now, in three-dimensional space, not one-dimensional space, how big is this paper? I think it was like 11 pages, but it was like double-spaced, so sorry, I just got to check something. Never mind. Not relevant. In three-dimensional space, we group the lattice sites into a set of hierarchical blocks of size Rn, which is roughly 2n times the Planck length. A block at level n plus 1 is made by grouping 8 neighboring blocks of size Rn. Okay, that's fair. The spins in each block are entangled to make a spin 1 triplet, and the spins of 8 neighboring blocks are again entangled to make a triplet of the larger block. So they're just kind of entangling outward in like a three-dimensional way. So you take a single block, and then there's the 8 neighboring blocks around it, you entangle all of them together, you get a spin triplet. And then the spin triplet there is entangled, again, 8 spin triplets around it are all entangled to make another spin triplet, and so on. And then here's the third part about the vacuum, the quantum gravity vacuum, how it should look. Part C. The standard model has many bound states other than positronium. A benzene ring is an extended bound state made from the fundamental fields and will leave its own imprint on the vacuum wave functional, but this imprint will be small since the benzene molecule is heavy. Fuzzball states with mass much larger than the Planck length are also heavy, so the effect of an individual fuzzball will be suppressed. But the number of these states is enormously large and offsets the suppression. That's the important part. So even though it takes a lot of energy to kind of spontaneously pop a black hole into existence in like a virtual way, and so because it takes so much energy, it's very, very suppressed, that it's a very, very unlikely thing to happen. There's like trillions upon trillions upon trillions with a trillion trillions of ways that you can do that, so they offset each other. So they say, thus we expect that the entanglement in the vacuum generated by the imprints of virtual fuzzballs will be very important. We quantify this entanglement by adopting the energy scales suggested by black holes. The vacuum with energy E equals 0 has the optimal entanglements between sites, which yields the lowest energy state. Yeah, okay, that makes sense. Suppose we have these optimal entanglements for all blocks up to those of radius R max. So remember, R max is, we haven't defined it yet. But no entanglement at larger scales. So basically they're saying that we have kind of like this optimal entanglement scenario for all of the black holes up to a certain size, and then we just have no entanglement beyond that size. The energy of such a state would be higher than the energy of the vacuum. We set the extra energy in the region of size R max to be of the order suggested by the black hole relation. R is proportional to GM. So they say that the difference in energy between the lowest energy state and the energy from having this entanglement in such a region of size R max is approximately equal to that radius divided by Newton's constant. So, and that's just a big energy difference, right? That's a lot of extra energy. Note that the non-perturbative objects being entangled have a mass approximately equal to the Planck mass. A quantum field with a mass equal to the Planck mass would have entanglement that decays exponentially over the distance roughly equal to the Planck length. This postulate, this first postulate here, says that the extended and numerous nature of black hole microstates leads to an entanglement that falls off more slowly. Because the black hole has a size, it's not going to fall off as 1 over the Planck length. This fall off may be characterized by the energy density, so delta rho is the energy density difference from the vacuum. And so that would just be the total energy divided by the volume. And because the energy goes as the radius divided by g, this is 1 over g times the radius squared, which falls off as a power of the scale R max rather than exponentially in the Planck length. And that's important. This is a power law, 1 over r squared, rather than exponential of, say, 1 over r or something like that. So, and I think that that's going to be key, but we'll have to see. Right. So with the above model of a gravitational vacuum, we can explain our central idea. It took them long enough. If space-time stretches too fast, then the semi-classical approximation breaks down. Okay. Consider the spins in figure 3a, entangled to yield the zero energy vacuum state. Now, suppose space stretches so that the spins S1 and S1 prime move away from the spins S2 and S2 prime. Then new spins S3 and S3 prime must get created in between, as in figure 3b. So what they're saying is you start off with A and space is this big, and then it stretches, so it becomes this big, and so there has to be new lattice sites in between them because you're making more space there. So now you can treat that as having more spin. There's spins there. To achieve the vacuum on the stretched space, the entanglement between the triplets T1 and T2 must decrease, and an entanglement of strength delta must be created between T1 and the new triplet T3. So there was entanglement between T1 and T2, but now they're further away, so that has to go down. But also now there's an entanglement between T1 and T3 because they're nearby. And so you have to create a new entanglement there because there can be a correlation. So, okay, let's keep reading. The entanglement between T1 and T2 can change only if signals can be exchanged between these two groups of spins. Ah, that's an important point. So if it expands too fast, then you kind of can't change the entanglement between the two, right? Because information only is communicated at light speed. If the stretching is slow, such a signal exchange is possible, and the vacuum of 3a will evolve to the vacuum state in figure 3b. It'll go from here to here, no problem. But suppose the stretching is so fast that such signals cannot be exchanged. Then the entanglement of T1 and T2 cannot break. By the monogamy of entanglement, that just means that if you have maximum entanglement between two things, then you can't have more entanglement with a third thing. By the monogamy of entanglement, T1 cannot then entangle with the newly created spin T3 in the manner needed for the vacuum wave functional. We will end up with an extra energy with our max of order the separation between T1 and T3. So the point is that because it won't be in the vacuum state, because you can't have the entanglement between T1 and T3. So if it stretches too fast, then the entanglement between this state on the left and the middle state just can't happen. Which means, but that was necessary to happen to be in the vacuum state. Which means that this can't be in the vacuum state. It has to be in a higher energy state, and the energy state that it has to be in has energy proportional to the radius or the distance between them, right? By this equation here. So because they're not entangled and they need to be, there must be extra energy there because it just can't be in the lowest energy state. So we end up with extra energy. So let's keep reading. Consider a gas cloud that shrinks. Oh, did I miss a super chat? I think I missed a super chat. No, I didn't. Okay. Consider a gas cloud that shrinks to form a star. Space stretches a little in this process, very little, in the region inside the star, but light can traverse the star multiple times in the time taken for star formation. So the stretching is adiabatic and Einstein's equations will hold to an excellent approximation. So the point is it stretches slow enough that this will never be an issue. In a gravitational wave, the deformation of space cannot be considered slow, but since the wave is transverse, we find that the volume of space doesn't change. So a gravitational wave doesn't stretch space slowly, but because it's stretching it kind of like this way, the volume never changes. Thus, we do not need to create new spins of the type S3, S3 prime, and we will again find no violations of Einstein's equations. Right? But now consider the stretching of slices in gravitational collapse. So let's go back up to this picture. Gravitational collapse. These slices are getting stretched a lot, right? Light signals cannot go from point A inside the horizon to point B just outside. So you can't send a signal from A to B, right? That's what it means for one thing to be inside the horizon and for the other to be outside the horizon. In fact, signals from A cannot even reach point C, which is at the same radius as A, since the light cones point purely inward inside the horizon. So this is saying, actually, you can't even get from A to C, right? You can only go from A to, like, the singularity and from C to the singularity, but you can't go from A to C, even though they're both inside the horizon. No, this doesn't really have anything to do with... Well, they haven't mentioned DESI once. Which is at the same radius as A, since light cones point purely inwards inside the horizon. Thus, in a region of size Rmax, which is proportional to GM being the mass of the black hole, on the good slice T2, that was the middle one. Let's go back up. The good slice, that's this one. On the good slice, the non-perturbative fluctuations of the vacuum will not be able to reach their vacuum entanglements, because they won't be able to talk to each other, right? These fluctuations will be in a state with an extra energy, which is roughly proportional to the mass, because the size of the black hole is proportional to the mass. In the later slice T3, space has stretched further inside the horizon, and the new stretched segment contributes a further energy proportional to the mass again. Thus, the good slices of the semi-classical geometry do not describe different foliations of a spacetime with mass m. Instead, the energy along these slices rises by m when the time at infinity is advanced by some amount of time proportional to m. Delta t is gm. The energy along these slices, the good slices of the semi-classical geometry, do not describe different foliations of a spacetime with mass m. Yeah, okay, so they're saying that the energy on each subsequent slice of space, or of spacetime, gets higher. Since energy is fixed at the value m, the quantum gravity wave functional cannot evolve semi-classically along this foliation. So I guess what this is saying is that the spacetime can't evolve according to Einstein's field equations because the energy is increasing, even if the energy is fixed, and that means that you have some sort of contradiction. Let's keep reading. If the evolution cannot proceed in the semi-classical manner of figure 1, what happens instead? So this is basically saying that if you take the semi-classical understanding, then you would have that the energy is increasing without bound. But we know that that can't be the case because the total energy is fixed, so something else has to be going wrong. We need a non-semi-classical evolution inside the black hole. So if the evolution cannot proceed in the semi-classical manner of figure 1, what happens instead? The Planck scale fluctuations have not been able to reach their vacuum entanglements, and thus show up as real excitations carrying the energy delta E on the space-like slice, figure 4. So each one of these will have a real energy on the space-like slices. This is within the event horizon, by the way. When these non-perturbative excitations link up in inappropriate ways, we obtain one of the fuzzball states depicted in figure 2. Okay, so this is actually what the fuzzball is. Kind of neat. The non-perturbative KK monopoles of figure 2b has a mass proportional to RC squared. I don't know what RC is, but yeah, I don't know what the C stands for. Well, it's proportional to some quantity squared. Fine. Thus, we get a lower energy for KK monopole fluctuations that are located close to a place where the scalar. Thus, we get a lower energy for KK monopole fluctuations that are located close to a place where the scalar quantum reduces the size of this circle. Oh, it's the radius of the circle. It's the radius of the circle that we were talking about. It's this. It's the radius of these circles here. The non-perturbative KK monopole has a mass proportional to RC squared. Thus, we get a lower energy for KK monopole fluctuations that are located close to a place where the scalar quantum reduces the size of the circle. So remember, in the compact direction, the kind of curled up direction of the curled up string theory direction, you get oscillations in like the size of that curled up string theory direction, and in places where the curled up size is smaller, you get reduced energy. So you get a lower energy fluctuations that are near those places with the smaller curled up dimensions. And so they're saying that time evolution will favor such configurations as the ones with lower energy, thus encoding the information of the collapsing shell into the wave functional over the space of allowed fuzzballs. So what are they saying? Coding the information of the collapsing shell into the wave functional. Okay, so what's happening, if I'm understanding this properly, is that essentially you're going because of the collapse, like the collapse of the black hole, or the fuzzball in this case. There's going to be certain places that will have a smaller value of this kind of scalar quantum that tells you about the size of this circle, and where those places are, and at various and when they are, that will tell you that in some sense encodes information about how the collapse is happening. And so because the time evolution prefers those places with lower energy, kind of settling into a lowest energy configuration, the actual behavior of the collapse will encode that special information about where the lowest energy configurations are, and that will tell us something about the collapsing shell in terms of the fuzzballs. The fuzzballs are the actual things that have the differing values of the or differing sizes of the differing radii of the circles. So this is to say that somehow we're encoding information of the collapsing matter, like the dust or whatever, into the description of the quantum description of the state, which is described in terms of fuzzballs. Seems complicated, but plausible. Hopefully they'll explain better. Actually, let's read the caption of this picture. The fate of the collapsing shell with our new picture of gravitational vacuum. Entanglements between Planck scale fluctuations are unable to relax to their vacuum values for the scales of order the horizon radius. This leads to the creation of on-shell non-perturbative objects, black dots, on the evolving slice, which then link up to create fuzzballs, upper slice of a kind in figure 2c. Okay. So, they have some stuff about cosmology. I'm just checking how much we have left. Good. Okay. So, wait a minute. Did I understand what was going on properly? Yeah, okay. So we have a... Yeah, let's think about this just a minute. Well, maybe they'll explain. Otherwise, I'll go back and think about it. So where else do we get fast stretching? In the expansion of the universe at the scale of the cosmological horizon, h is the Hubble constant, which tells you how fast the expansion is. A dot, or A, is the size of the universe, and A dot is the time derivative of the size of the universe. So this is just a definition. H inverse is just equal to A dot over A. Einstein's equations will work well for distances much smaller than the Hubble radius. The Hubble radius is just basically the size. It's a length scale determined by the expansion rate of the universe, which has something to do with basically the amount of time that light would have to take to get there and back. Or actually, it's just the amount of time that it would take light to get there. So this is saying that Einstein's equations work well for distances smaller than the Hubble radius. Since light can cross this scale r multiple times over the expansion time scale h inverse. This is no longer true at distances much greater than the Hubble horizon. So entanglement across this scale need not be in their optimal vacuum form. Now, that's an interesting observation. You have a fluctuation here, might be entangled with something very, very far away in a much, much, much more distant part of the universe. Well, now they can't talk to each other anymore. But this implies an extra energy is created over the volume of the cosmological horizon. This is the volume, it's just this Hubble radius cubed. And so, what they're claiming is that you get some extra energy. You get some extra energy in that volume, and that energy is roughly proportional to the radius of the Hubble, or to the Hubble radius divided by g. This corresponds to an extra energy density, which amounts to roughly the Hubble radius squared divided by g, which they call rho sub c, where rho sub c is the closure density. That's how much energy it takes for the universe to close up into a compact thing, which is interesting. To see when we will induce this extra energy, we note a new twist that comes with cosmology. At distances larger than the particle horizon is the distance at which you will never be able to receive a signal from something ever. At distances larger than the particle horizon, RP, that's what this is. It's an integral of from t equals 0 to sometime t. It's just the whole thing. Signals have not had time to travel to establish the entanglements of figure 3a. So for distances, I think that's the particle horizon. Let me just double check, because I always get this one confused. The particle horizon is the maximum distance from which light from particles could have traveled to the observer in the edge of the universe. Yeah, I got that one confused with the cosmic horizon. So this is the distance by which we could have received signals by now. So when stuff is at distances larger than the particle horizon, you could have never received a signal from something by now from the beginning of the universe. So for distances greater than the particle horizon, fast stretching will not result in the entanglement problem, because they couldn't have talked to begin with. Yeah, they haven't even established entanglement yet, right? So if they haven't even established entanglement, then even if they stretch faster, there's no extra issue. The constraint in the above paragraph then says that delta rho is not equal to 0. That's this. At least that's what it's supposed to be. Only if the particle horizon is bigger than the Hubble horizon. So if the particle horizon is bigger than the Hubble horizon, then that means that there's a region where there would have been enough time to establish entanglement, but then the universe is expanding too fast for that entanglement to break. But if the particle horizon is smaller than the Hubble horizon, then the stuff that is expanding too fast for the entanglement to break is too far away for the entanglement to ever been established in the first place. And then they reference this paper 4. They say in 4 it was noted that for the radiation phase, where the scale factor, the size of the universe, goes as the square root of time, we have that the particle horizon is equal to the Hubble horizon, while for the dust phase, this is what we're in now, or this is what we were in 5 billion years ago. The dust phase is when the universe is dominated by matter rather than dark energy. We have that the particle horizon is roughly twice the Hubble horizon. Thus, in the radiation phase, when the universe was dominated by light, we will not get much extra energy from fast stretching, which accords with the tight constraints on this phase from Big Bang nucleosynthesis. The radiation phase is very tightly constrained. In the dust phase, on the other hand, we will get an extra energy density, which is roughly equal to rho sub c. This extra energy is of the correct order to account for dark energy we see today. The transition from radiation to dust induces a change in the entanglement profile of the non-perturbative virtual fluctuations. The dark energy associated with this change might yield the early dark energy that has been postulated at the radiation-dust transition to account for the Hubble tension. That's really cute. So, okay, we'll read the summary and outlook, and then we'll talk about it. Hawking's paradox demands that Einstein's gravity must fail when a horizon forms, even though curvatures are low everywhere in a good slicing through the black hole geometry. We have given an explicit model for the gravitational vacuum which leads to such a failure through the creation of the energy when space stretches too fast. This energy induced by non-adiabatic expansion is reminiscent of the phenomenon of particle creation in curved space, which occurs when vacuum fluctuations of the type in figure 2a are unable to attain their optimal vacuum form due to quick stretching of space. But as we noted above, the quantum fields describing these small fluctuations are unable to reproduce the microstates of black holes. In string theory, these microstates are fuzzballs composed of the non-perturbative objects of figure 2b. Black hole microstates are extended and numerous. So again, the important point is that there are a lot of these, which accounts for the fact that they are really, really rare. Virtual fluctuations corresponding to these microstates leave an imprint on the vacuum in the form of slowly falling entanglement between the virtual fluctuations of the non-perturbative objects of figure 2b. So as they stretch, you have more stuff there, and because the entanglement takes time to break, you get extra energy. Since these objects are heavy, their fluctuations relax quickly to their vacuum form when possible, screening such objects from view in slow processes like star formation. But in the black hole geometry, the light cone structure disallows such relaxation, leading to a nucleation of fuzzballs in place of the traditional semi-classical stretching of slices. Fast stretching also occurs at the scale of the cosmological horizon with potentially observable effects. The picture of the gravitational vacuum also alters our thinking about the cosmological constant problem. String theory possesses a large number of compactifications with Planck scale vacuum energy density, and anthropic arguments are then invoked to select one with small lambda. But in fuzzballs, the compact directions are not trivially tensored with the non-compact ones, thus virtual fluctuations of these black hole microstates should imbue the vacuum with a similar non-tensored structure. Instead of asking for the energy of a given compactification, we should ask for the energy of the state with optimal entanglements between the structure of the type in figure 2b, created by the different ways of pinching off the compact directions. The black hole horizon is a closed trapped surface, while the cosmological horizon is a closed anti-trapped surface. The two are related by time reversal. In our picture, the same entanglements which resolve the information puzzle also give rise to dark energy. Thus, we may have already seen quantum gravity through astrophysical observations. Super cute. So, I mean, the black hole stuff is interesting, but slightly less interesting to me, to be honest, because it's very hand-wavy about how we actually get the information back out from the black hole. Because, you know, it's a very qualitative description. But the qualitative description that they gave for the cosmological relationship about the energy gained from the breaking of entanglement, the forced breaking of entanglement, that was purely qualitative. But the important point is that it's the scaling factor that matters, and the scaling factor exactly matches what it needs to be. That namely, this critical energy is h squared, and that's what it needs to be. It's of the order h squared over g. And so the fact that this kind of straightforward model basically amounts to a depiction of dark energy where you have a radiation-dominated phase of the universe, which is the first few seconds, I think. Or I guess the first few 100,000 years, I guess. I can look, but radiation-dominated era cosmology. Okay, so about 47,000 years. For the first 47,000 years, you have basically no dark energy. And then after that, dark energy arises in a dynamical way, because this is like a smooth effect. And so this is just another inclination that dark energy should be dynamical. At least it's kind of expected that it's dynamical, because we have it turning on slowly as matter begins to dominate over radiation. It also seems to account for the actual cosmological constant rather than rather than just kind of having to put in the cosmological constant by hand, which is really, really nice. Of course, you need to develop this more clearly because these are all kind of like approximate statements. They're all kind of order of magnitude type estimates, or they're all kind of like proportionality estimates. Nonetheless, it is a fascinating paper. I'm glad I read it, and not the one that won second prize. So if you want to take a look at it, the paper to read is Space Cannot Stretch Too Fast by Samir Mathur. It's a very, very interesting paper. We just finished it. If you want to go back and rewatch or reread the paper with me, this will be live on YouTube in 5 minutes, because we're going to end the live here. So for everybody who's been watching, for everybody who's been enjoying, I'm glad that you've been here. I'm glad that you enjoyed and followed along with us. And I'll see you guys tomorrow for Ask a Physicist. Remember, Wednesdays are Ask a Physicist days, so come by, ask your basic physics questions. I will be happy.